So if we continue our discussion of redox reactions, we already said that in a redox reaction, electrons are transferred from one component in the reaction to another. Now we're going to look at how we used our oxidation states that we know how to determine in order to identify both an oxidation and a reduction process in a reaction. The way that we will identify redox reactions is by looking for a change in the oxidation state of a component from the reactants to the products. So that as we look at the oxidation states for an atom at the beginning and the oxidation state for the atom at the end, we're going to find that there's a difference. Oxidation occurs when we have a loss in the number of electrons, and that's consistent with having an oxidation state that increases. So when we look at oxidation states, an increase might be an oxidation state that goes from 0 to +2. An increase in our oxidation state might be one that goes from +2 to +4. An increase in our oxidation state might be one that becomes less negative. So for example, it could go from -4 to -2. All of those changes from the oxidation states at the beginning of the reaction to the oxidation states at the end would be consistent with an oxidation process. Reduction, by definition, is a gain in the number of electrons, and we will identify reduction processes by looking for an oxidation state that decreases during the course of the reaction. A decrease in our oxidation state might be a change where we see an oxidation state of 0 at the beginning that becomes -2 at the end. Maybe we have something that changes from +2 to 0, or maybe something changes from +4 to +2 during the course of a reaction. All of those are consistent with decreases in the oxidation state, which allow us to recognize a reduction process. The mnemonic that we often use for oxidation and reduction processes is oil rig. Oil stands for oxidation is loss. Rig stands for reduction is gain, reminding us about how the electrons are going to change during these processes. So if we look at some examples where we can use oxidation states in order to identify oxidation and reduction processes. The first one is a reaction between carbon and sulfur to form carbon disulfide. Pause the video and determine the oxidation states of the starting materials and the product. Identify your oxidation process. Identify your reduction process. So what you should have determined are oxidation states as follows. The carbon at the beginning of the reaction had an oxidation state of 0. The sulfur at the beginning of the reaction also had an oxidation state of 0. Anytime we have something in an elemental state, its oxidation state will be 0, just like both of our starting materials here. In carbon disulfide, we had to set up an equation in order to solve for the oxidation states, and we set up that equation on the rules packet that we previously went through. Carbon's oxidation state is +4, sulfur's oxidation state is -2. So now as we look at the changes during the course of the reaction, my carbon starts out with an oxidation state of 0, ends up with an oxidation state of +4. That means that its oxidation state has gone up, and that's consistent with an oxidation process. Sulfur has started out with an oxidation state of 0 and ended up with an oxidation state of -2. That means that its oxidation state has decreased, and that's consistent with a reduction. So that during the course of this reaction, we could say that the carbon has been oxidized and the sulfur has been reduced. The carbon has lost electrons and the sulfur has gained electrons. In the next reaction, pause the video again, determine all the oxidation states for the materials, identify your oxidation process and your reduction process. So we see that some of our oxidation state change during the course of the reaction and some of them remain the same. Specifically, my magnesium starts out with an oxidation state of 0, ends up with an oxidation state of +2. That means that its oxidation state has increased, and that's consistent with an oxidation process where it will have lost electrons. During the course of this reaction, my hydrogen in water starts out with an oxidation state of +1, ends up with an oxidation state of 0 in my hydrogen gas. That means that its oxidation state has decreased, and that's consistent with a reduction during the course of the reaction. So in this reaction, the magnesium has been oxidized and the hydrogen has been reduced. Notice that oxygen's oxidation state remains at -2 during the course of the reaction. I also have some hydrogens that maintain that oxidation state of +1. One more time, I want you to pause the video and I want you to determine the oxidation states for each of the atoms in this reaction as calcium oxide and carbon dioxide are converted to calcium carbonate. You should have gotten the following oxidation states. During the course of this reaction, calcium starts out with an oxidation state of +2, ends up with an oxidation state of +2. Oxygen starts out with an oxidation state of -2 in calcium oxide, -2 in carbon dioxide, -2 in my product. The carbon in my carbon dioxide starts out with an oxidation state of +4. It also has an oxidation state of +4 in my product. Because all of my oxidation states have remained the same from start to finish, I would conclude that this is not a redox reaction. There is a chemical reaction that has taken place, but it's not one where the number of electrons has changed. All of my components have the same number of electrons at the beginning and the end of the reaction. Let's look at an example exam question that I could ask you, and that could be this one here. Which of the following is not a redox reaction? Where choice A would be this reaction, choice B, this one, and choice C, this one. In order to answer this question, we don't necessarily have to determine all of the oxidation states for all of the components in the reaction. In order to identify which one is not a redox reaction, we just have to know that there's not a change in the oxidation state from start to finish. So one way that we could approach a question like this is by looking for free elements that are present in our reaction. For example, we know that the carbon at the beginning of this reaction has an oxidation state of 0. And because my carbon is present in a compound at the end of this reaction, I know that its oxidation state is most simply not 0. That means that without even calculating the oxidation states for the carbon, I know that there's been a change in the oxidation state for the carbon. In question B, magnesium starts out in an elemental state. That's rule 1 in our rules for oxidation state determination. So I know that its oxidation state is 0. At the end of the reaction, I know that magnesium is present in a compound. So again, most simply, I know that its oxidation state at the end of this reaction is not 0. I can do the same thing for the hydrogen in this reaction. I know that the hydrogen is present in water at the beginning of my reaction, so I know that its oxidation state is not 0. At the end of the reaction, I see hydrogen present as a free element, so I know that in that case, its oxidation state is going to be 0. So I know that I have a change from something that's not 0 to 0. So even though I don't know what this oxidation state is, just by looking at this reaction, I know that it's not the same on the product side of the reaction, so I do know that there's been a change in the oxidation state in this reaction. There's no simple shortcut here for this reaction. In order to confirm the oxidation states, we would have to go through and calculate all of them. But when we have free elements present in our reaction, like in choice A or choice B, we can use that 0, not 0 idea to look at our components at the beginning and the end of the reaction to quickly recognize a change without looking at the full details of what that change is going to be. So to answer that exam question, which one of the following is not a redox reaction? It would, of course, be choice C. Now, the final piece of this is the identification of what's called an oxidizing agent and a reducing agent. The idea of the oxidizing agent and the reducing agent get at the fact that oxidation and reduction processes always go hand in hand. In order to have oxidation, you must have reduction. In order to have reduction, you must have oxidation. So when we look at an oxidizing agent, by definition, it allows for the oxidation of another substance. The role of the oxidizing agent is to allow something else to be oxidized. That means that during the course of the reaction, it is allowing something else to lose electrons. It is allowing something else to lose electrons. That means that the oxidizing agent is going to gain electrons during the course of the reaction, and that's associated with a reduction. So the oxidizing agent is your component that gets reduced during the course of the reaction. So your oxidizing agent gets reduced during the course of the reaction. Now the opposite is true for the reducing agent. It will allow for the reduction of another substance. So the reduction means that that other substance is going to gain electrons. In order for that other substance to gain electrons, your reducing agent must be present in your reaction to lose electrons. The loss of electrons is oxidation. So that means that your reducing agent will be oxidized during the course of the reaction. The reducing agent facilitates the reduction because it will be oxidized. The oxidizing agent facilitates an oxidation because its role is to be reduced. So think about that for a moment. Reread those definitions and make sure you understand the role of an oxidizing agent and the role of a reducing agent. Then look at the two examples here. Determine your oxidation states at the beginning and the end of each of these reactions. Identify the component that has been oxidized, the component that has been reduced, the oxidizing agent, and the reducing agent. Beginning of this reaction, zinc has an oxidation state of 0 because it's a free element. At the end of the reaction, we know that its oxidation state is not 0 because it's an ion. Specifically, its oxidation state will be a +2. At the end of the reaction, iron's oxidation state is 0. We know that it's not 0 over here, so that allows us to quickly identify this process as a redox reaction. When we look at the changes that we see in this reaction, zinc starts out with an oxidation state of 0, ends up with an oxidation state of +2. Its oxidation state has gone up. That's consistent with an oxidation process. Iron starts out with an oxidation state of +2, ends up with an oxidation state of 0. Its oxidation state has decreased, and that's consistent with a reduction process. Now, the final thing that we need to identify is the oxidizing agent and the reducing agent. So what we know right now is that our zinc has undergone the oxidation. If you look back up at your definitions, the role of the reducing agent is to be oxidized and allow for your other component to be reduced. So because we know that zinc has been oxidized, we also know that the zinc is our reducing agent in this reaction. Our iron has undergone the reduction. And so when we look back up at our definitions, we see that the oxidizing agent, its role in the reaction is to be reduced, allowing something else to lose electrons. The oxidizing agent gains those electrons so that my other component can lose those electrons. So in this reaction, I know that my iron has undergone the reduction. My iron then also plays the role of the oxidizing agent. Pause the video again. Determine your oxidation states for each of the components in this reaction. As we look at each of these components, We see that we have our components present in an elemental state at the beginning of this reaction and in a compound at the end of the reaction. So we know without even calculating those oxidation states that this is a redox process. Magnesium starts out with an oxidation state of 0, ends up with an oxidation state of +2. That's consistent with an increase in its oxidation state, which is an oxidation process. The oxygen starts out with an oxidation state of 0, ends up with an oxidation state of -2. That's consistent with a decrease in its oxidation state, and so that's going to be a reduction. So overall, we know, first of all, that my magnesium during the course of this reaction has undergone the oxidation. That means that in this reaction, my magnesium has been oxidized, therefore it lost electrons and allowed my other component to gain those electrons. So my magnesium was oxidized and plays the role of my reducing agent. My oxygen, we determined, had undergone the reduction. So that means that my oxygen was reduced. It gained electrons during the course of the reaction, and because it was there to gain those electrons, something else was able to lose the electrons. So that means that my oxygen in this reaction played the role of the oxidizing agent.